The Goroutine, this is application level lightweight thread with a stack size about 2 kilobytes. The maximum stack size about 1 gigabyte for x64 and about 250 for x32 system. Unlike OS thread, the Goroutines has a little size 1 megabyte OS thread and versus 2 kilobyte Goroutine. Goroutine does not store the state of register of cores, and also the Goroutine does not create any OS threads. It uses existing threads. The OS scheduler is preemptive. It means it decides by its own when to switch the context from one to another OS thread. And in comparison to it, the Golang scheduler was cooperative before 1.0.14, and it means it switched the context from Goroutine only when the Goroutine was blocked on mutex, channel, or system call. And in new versions of Go, it became preemptive cooperative to not idle on endless loop with useless work. So the GMP model. OS scheduler has three main things. So the first, Goroutine, also machine, which is OS threads, which can execute the Goroutines, and the processor for Goroutines and OS threads. The processor is a virtual core. Also, scheduler has a global run queue, general for all scheduler, and local run queues for each combination of machine and processor. The amount of threads is configured by GoMax procs, and it has a default value equals to num_cpu, which is the amount of available cores. And the GoMax procs can have a value between 1 and num_cpu. So the states of Goroutines. There are three of them. The first is waiting, when the Goroutine is blocked by when the Goroutine is waiting for something like unblocking the mutex or channel or system call. Also the runnable state, when the Goroutine is ready to run, but it cannot because it is waiting in local run queue because the OS thread is busy. And also the executable state, when the Goroutine is executing. There are two types of system calls. First, asynchronous, and it's uses network poll if it is available in operation system. And there is simple flow. So while the async call happens, the goroutine gets to network poller, waiting for a response from network, for example. When the network is get, the goroutine comes back to the local run queue. The synchronized call is harder. It is happening when you use C code from CGO package or when you work with files. So the flow is when the goroutine blocked by synchronized call, the goroutine together with the thread where it is executing, they detached from the processor. Then when the system call finished, the goroutine gets to the local run queue of the old processor. And I forgot to mention that when the OS thread is detached, the process gets a new thread from the thread pool. So, work stealing. This process happens when the OS thread and the processor does not goroutines on the thread and in the local run queue. And in this case, it looks for goroutines. So first it comes to the global run queue. If there is no one goroutine, then it starts to look for all processors in random order. And if no one of processors has goroutines in their local run queue, then our OS thread go to sleep. But if the goroutines were found, then it takes half of goroutine, but no more than 32 goroutines. So runtime methods. There are, as I remember, GC method, which forces the garbage collector to start. Also go exit, which finish the goroutine. Go max procs, which set the amount of available threads. Num goroutines, which return amount of all goroutines in program. And go sched, which switch context from the current goroutine. To synchronize goroutines, we can use primitive synchronization primitives like mutex, LRV mutex, waiting group. To avoid the leak of goroutine, we can use different strategies like transferring the context to the function goroutine to manage lifecycle, or to not forget the default in a select expression. Also to not forget close the channels when they are not used, and also use pprof to monitor goroutines and the leakage, and also to control the add and done calls while using the wait group.